The last application we're going to look at for these exponential and logarithm models are going to be Newton's law of cooling sort of scenarios. So Newton's law of cooling suggests that over a period of time, objects are going to cool, and that what we can do is we can use this relationship that the temperature T is going to be equal to C plus T sub naught minus C e to the KT, right? C is going to be the ambient temperature or the constant temperature around the object. So if we put it in a refrigerator or we put something outside or we put it in our house, that's going to be that constant or ambient temperature. T sub zero is the initial temperature, and K is going to be the negative constant that's going to be associated with cooling the object. So um, some problems that would ensue. Let's say we pull a cake from an oven and the cake has a temperature of 210 degrees Fahrenheit. It's left to cool in a room that has a temperature of 70 degrees Fahrenheit. After 30 minutes, the temperature of the cake is 140 degrees. So it tells us that the initial temperature is 210 and this ambient temperature is 70. It also tells us after 30 minutes the temperature of the cake. So let's use Newton's law of cooling to find a model. Then we could try to find the temperature after 40 minutes and then try to find the temperature when it'll be 90 degrees. So like we said, C, which is going to be the constant temperature, is going to be 70 degrees. T sub zero is going to be 210. And we also know that T at 30 is going to be equal to 140. Okay, so these are all like the initial sort of conditions or the initial values that were given for this. So we're going to substitute everything back in up here, and we should be able to solve this for K. So our temperature T is going to be 140, and that's going to be equal to C, which we said was 70, plus the initial temperature, which was 210, minus C, which in this case is 70, and then e to the KT, but we know that T was 30. All right, so now we just solve, just like we have done many, many times so far in this section. First thing we're going to do, subtract 70 from both sides. And then I'm also going to evaluate that 210 minus 70. So I end up with 70 is going to be equal to 140 e to the 30k. Excuse me. Then we can divide both sides by 140. We know 70 over 140 is just going to be a half. So we end up getting 1/2 equals e to the 30k. We can take the natural log of both sides. So ln of a half is equal to e to the 30k, or ln of e to the 30k. Then we can divide by 30 to solve for k. All right. Now, we're going to just go ahead in our calculators. We're going to approximate k by just throwing this animal into our calculator. So we're going to clear this. And we have the natural log of a half. And we're going to divide that by 30. We should get a negative number. We get negative 0.0231. All right, so that's going to be our decay constant for this. All right, that's actually going to help us to tell what the temperature is going to be. Okay, so K is going to be negative 0.0231. And so our model T is going to be equal to whatever C was. All right, so, and all I'm doing is I'm just going back up here and I'm substituting back in for everything that I know. Okay, so that's going to be T is C, T0 minus C, e to the KT. So 70 plus the quantity of the initial temperature, 210 minus 70, e to the negative 0.0231 lowercase t per time. Okay. The other thing we probably want to do is we just want to subtract this and get 140. All right. So in reality, our function, which I'll just call t of t, is going to be 70 plus 140 e to the negative 0.0231t. All right. That's the hardest part of the problem. After that, all we're going to do is just use that function. Okay, so for letter B, what is the temperature after 40 minutes? Okay, so all we're going to do is substitute 40 back in for T. So this is B. So T at 40 is going to be 70 plus 140 e to the negative 0.0231 times 40. And now we can just plug that into our calculators. All right, so we would have 70 plus 140 e to the negative 0.0231 times 40. I always have to put parentheses. And that's going to be 125.57 degrees Fahrenheit. So that would be 120, I forgot already, 125.57. And that would be in degrees Fahrenheit. Okay. All right. Now, the last part of this problem is going to be when does it take the temperature to be 90 degrees? So we're just going to set 90 equal to capital T and solve it. All right. Just to kind of get a ballpark figure, remember we said that after 30 minutes, okay, the temperature cools down to 140, all right? And then after 40 minutes, the temperature is 125. So it probably, if we're going sort of in like that pattern where we get 140 and then like 125, etc., we're probably looking at somewhere between like 60 or 70 minutes or something like that, just guesstimate. But all we're going to do is we're going to substitute that 90 back in. So 90 equals 70 plus 140 e to the negative 0.0231 t. We're going to subtract 70 from both sides. And so we get 20 equals 140 e to the negative 0.0231 t. We're going to divide by 140. So 20 over 140. All right, that's just going to become 1/7. So 1/7, just by dividing it out, is equal to e to the negative 0.0231 t. We're going to take the natural log of both sides because we need to get rid of an e. We're going to divide, because the L and the e's cancel each other out, we're going to divide by negative 0.0231, and that'll help us solve for t. Okay. So in our calculators, we have the natural log of 1/7 divided by negative 0.0231, and that gives us 84.238. Okay, so I'll just say 8424. Okay, so 24, and that's in minutes. Okay, so that's how long it's going to take for the cake to get down to 90 degrees Fahrenheit. Okay, all right. One last problem with respect to Newton's law of cooling. A bag of frozen peas initially has a temperature of 20 degrees Fahrenheit. This time it's not cooling, but it's actually warming up. It's left in a room. It's left to thaw in a room that has a 72-degree temperature. Right. After 8 minutes, the temperature of the bag is risen to 39 degrees. After how many minutes will the temperature of the bag be 65 degrees? All right. So another problem where we have to go through and use our formula. Okay. So let me just write out the formula. T is equal to C plus. We're going to say. If we look back up at our formula, I just forgot which symbols we used. So we use T sub naught minus C. All right, so that'll be T sub naught minus C e to the KT. All right, so that's the formula we're going to use for this. That's our Newton's law of cooling. T sub 0 is going to be equal to 20. Okay, that's pretty easy to see. The ambient temperature, C, is going to be equal to 72. And finally, we want to figure out what happened. We know that T at 8 is going to be equal to 39, because it said after 8 minutes, the temperature. So essentially, what we're going to do is we're going to have to find the function, and then we're going to have to figure out when the temperature is going to be 65 degrees Fahrenheit. All right, so let's get to it. So our temperature T, which we know to be 39 after 8 minutes, is going to be equal to 72 plus T sub 0, okay, which is going to be the initial temperature 20, minus 72, which is the ambient temperature, e to the kT, but we know that after 8 minutes, it's going to be 39 degrees. We're going to subtract 72 from both sides. And if we do that, 39 minus 72, just to be sure, because I'm recording. All right, that's going to be negative 33. So we get negative, let me just verify that, 39 minus 72. Yep, negative 33. And then 20 minus 72 is negative 52, e to the 8k. We're going to divide both sides by 52, or negative 52. And there's nothing, I think there's no common factors between them. But we are going to take the natural log of both sides. So ln of, we're going to say 33 minus 52. That's 33 over 52 is equal to ln of e to the 8k. And then we can just divide by 8. So ln of 33 over 52 divided by 8 is equal to k. And we have ln, so we punch this in, ln of 33 over 52 divided by 8. All right, that gives us negative 0.0568. Right, so k, negative 0.0568. Now that's going to help us with our function. So now we can just substitute everything back in to get a generic function for this. Going back up here, T is going to be equal to, so remember we said the constant temperature C was 72, plus the initial temperature was 20 minus 72 e to the negative 0.0568 T. Now, if we subtract this, that's going to be a negative 52. All right. So our function, which I'm going to call T of T, is going to be equal to 72 minus 52e. All right, so I'm just copying this down, negative 0.0568t. All right, now that's our generic function. And the question asks us, after how many minutes will the temperature be 65 degrees? So all we're going to do is just plug in 65 and solve for t. And this should be pretty easy by this point. We've done this lots of times. We're going to subtract 72. We're going to divide by 52. All right, so 65 minus 72, that's going to be a negative 7 equals negative 52e to the negative 0.056et. We divide by negative 52. That's going to be 7 over 52 equals e to the negative 0.0568t. We can take the natural log of both sides, right? Just like we've done lots of times. ln's and e's cancel each other. We're going to divide by the negative 0.0568. All right. And mercifully, this is the last time we'll have to put this into our calculators, at least in this video series. And we can be able to solve for t. All right. So t is going to be approximately, so we have our ln of, what do we have? 7 over 52. And we're going to divide that by the negative 0.05, I think it was 68, yep, 0568. And it looks like it's going to be 35.31 minutes. Okay, so all right, let me make that look like a real minutes as opposed to like some sort of squiggle. All right, so that's it. Okay, so lots of applications that we can use, and we haven't looked at all the applications. Okay, there's a lot more for exponential and logarithmic sorts of modeling, but we looked at some of the most prevalent. Okay, so that actually ends this whole chapter with exponential and logarithmic sorts of functions. So we're actually going to move away from algebraic sorts of applications, and we're going to start moving into trigonometry for the next few chapters of the course. So it's going to be a bit of a shift change after this video. There's going to be more concepts, but the algebra is going to be a little bit easier than the stuff that we saw in this section.